Now we'll hear about the Three Horsemen, AI agents know how to lean, from Nehal Patel from G Research.
Thank you. It's an absolute pleasure to be here. I'm Nehal. G Research is based in London. It's a quantitative finance firm, which means that the people there build models to predict prices for stocks and other securities. And I work in an area called the Innovation Group. And I was asked about a year ago to take a look at lean and try to figure out what is this thing? Could it be relevant for G Research? And in particular, to focus on the intersection of lean and AI. And my approach is pretty experimental. I make prototypes, I do experiments. So what I wanted to do was share the results of a small experiment that I did a couple of weeks ago. It's a very simple experiment, but I found the results interesting. And it has to do with something called the Putnambench. So I'm going to cover a lot of stuff that many people might already know, but the Putnambench is a collection of 660 problems that have been taken from the Putnam exam, which is a university exam that's given to students in the US. And a problem might look like this. So this is from the 1962 exam. The students asked to prove an identity. It's graded by a human. They get a score from 0 to 10. And there's 12 problems on the exam. So there's a 3-hour section in the morning, a 3-hour section in the evening, in the afternoon. And usually the first problem in the section is the easiest and the sixth is the hardest. And so what the Putnambench has done is taken these problems and formalized them. So this is what the formalization of that specific problem looks like in the Putnambench. So you have the formalization, you have the proof that's left as by sorry, and then different AI systems try to evaluate how they're doing by seeing if they can remove the sorry. So the Putnambench has a leaderboard where a lot of these AI systems have been able to post the results. So this is the leaderboard as of, I think, today. It moves pretty fast. The current leader is a system called Aleph Prover from a startup called Logical Intelligence. Hilbert is from Apple, Seed Prover is from ByteDance, Axe Prover is from Axiomatic. And just to give you a sense for how fast this moves, I think this leaderboard, if you looked at it at the beginning of the year, the top score would have been 7. So this is the amount of progress that's happened. Yes, I think so. It's like 4 to 7. I can't remember the exact number. So this is basically people are saying that this exam has been saturated. Okay. And so this slide is sort of the top line slide for my experiment. Basically, I was interested in seeing how AI agents would perform on the Putnambench. And I'll explain what AI agents mean to me, how they work, how you'd use them for working with lean. That's sort of the process. But this is the top level result. So it says something like an agent, which is called Claude, when it uses a model called Opus 4.5, it scores a 203. So just to kind of put that in the leaderboard, that would put it in 4th place. And I don't think that's important, but people often wonder where that is. So that's its position. And so I guess the first question is, well, what is an agent? And so it's a piece of software that runs on your computer. In my notion of what is an agent, agent is something that I can download and run it on a computer. And there's 3 agents that I really like. I call them the Three Horsemen. There's one called Claude, which is from Anthropic, Codex, which is from OpenAI, and Gemini, which is not on this slide. It'll show up on some other slides, which is from Google. And when you use an agent, you can tell it to use a specific model. So there's different kinds of models. Some are slow and more expensive, but more capable. Some are cheaper and faster. So the top line says I'm using Claude with Opus, and I get a 203. Or I don't get a 203, it gets a 203. And so that's the first thing. There's 3 agents I use. And so what are these things? I kind of think of them as a first approximation. They're sort of the body. So the model is this brain and the body is this agent. And the way the agent works is it's able to do things for the brain. It's able to run commands on your computer. And I'll describe a little bit more about what that is. But one important point is that without the agent, you don't get any results. Like it's effectively zero. So, and by what I mean by that is many people when they use AI, they go to the website, they paste something in, they get the results. So if you took that formal statement from Putnam and you went to the ChatGPT website or the Anthropic website, you put it in, you asked it to create a lean proof, it would generate something that looks like lean syntax. It might look reasonable. You give it a compiler, it definitely wouldn't work. Almost surely you'd get a zero. Maybe 1 or 2 out of 660 would pass. And if you're clever, you might think, well, I'll just take the compiler errors and feed it back into the website and see what happens. And even that doesn't really bring much performance. I mean, the main issue is that premise selection. So it just needs to know, so these models know a little bit about lean, a lot actually, I would say. They understand tactics, they understand syntax, but they haven't memorized the 100,000 premises that you would need that are in MathLib, and so it gets stuck. There's no way for it to understand what premise it should be using, and so that's what's going on. And then there's the question: well, how are the agents able to do this? And we'll talk about that in a second. But I think the next thing is like it would just be nice to see what an agent actually looks like. So so this is roughly how I use agents. So it's I have VS Code open, I have a blank lean4 file, and I have an agent to the side. So this is a program running in a terminal. So this is just a terminal that's not on the bottom, it's just on the side, and it's something that you can interact with. And so what I'm going to show you is a very quick demo of not the agent solving a Putnambench problem, and actually the demo that I give my colleagues when they ask, well, what is lean? I actually use AI to show it to them, and I'm going to show you the same demo compressed. So the first thing I do is I give the agent a prompt. I tell it to do something, and I don't type that. I just dictate it. So the main thing I would say is that it's so much more fun to use AI if you just speak to it. So that's not hard to do. So you just you can give it a lot of information. You can be very redundant. So I'll put it up here. So basically, the demo, I'm interested in weaving. So I want to model weaving in Lean4. And if you think about what a weave is, the fabric has vertical threads, there's horizontal threads. And so I'm going to model weave, and I'm dictating this to the AI, right? It's not that I'm typing, I'm just telling it exactly like this. I could even interrupt myself. And so in my model of a weave, I want to model it as a function from z mod n cross z mod n to z mod 2. And the idea is that when these threads intersect, either the horizontal thread will be in front of the vertical thread or will be behind it. And this is what we're modeling. And we have a finite periodic weave. But now that I've defined a weave, I want to make some other properties of weave, like a balanced weave is a weave where the number of times the horizontal thread is in front is the same as the number of times it's behind. I can define other properties like a reversible weave, which is to say the weave should look the same if I flip it over. And then now that I've defined some properties of a weave, I can say the theorem, which is that a reversible weave is balanced. So I tell the agent, please do all of this in Lean4 and go for it. And so this will be a time-lapsed display of what happened. So after a few seconds, what it's done is read a few files. It's telling me what it's doing. So there's a lot of transparency in this agent. And at some point, it asks me for permission to make edits to my file. I give it permission, and it starts generating a proof. So you can see this is what the proof looks like. You can scroll down. And basically, there's definitions, and then it's it's basically formalized the topic that I was interested in. It has a proof that's been left by sorry. And then maybe, let's see, a minute or so in, 2 minutes in, it starts proving, and it has all kinds of problems, right? You can see all kinds of compiler errors on each side. It keeps going, it changes its mind about what the proof should be, and it's looking like a little bit better, still making some changes, and then eventually gets to a place where the entire file is warning free. And that's like the first 5 minutes of this demo, and it's usually a 1-hour demo. Because after that, I very quickly go into like, okay, well, let's use this agent and now start changing what we did. So let's take the weave and change it into a colored weave. And I show them how to do that. I then say, okay, now agent, create me a proof widget so that I can visualize my weaves, and off it goes. So it started with discharging a sorry, but it's now doing kind of functional programming for me. And then, I go and say, like, I want a Verso manual. So go to this website, this other GitHub project that uses Verso, figure out how it's using Verso, and then add it to my project so I can have a Verso manual. And off it goes, and it creates that. So there's a lot of different things. And then throughout the whole workflow, I'm doing many different kinds of things. I'll take that file, I'll ask the agent to refactor it into multiple files. These agents, even though they're text programs, you can paste images into them. It sort of creates a little notation for it. So I might go to the web and like select some images and say, can you figure out how to model a houndstooth pattern or a herringbone pattern? And then, I can also, as it's going along, ask it questions about lean. Like when I see something I don't understand, like, okay, what is COE sort? Like, what is that doing? Why is it there? Can you give me some examples? I can kind of use the agent to help learn some obscure things about lean that I don't know about. And when it gets stuck, I can ask it, okay, I don't know why you're stuck, but can you just put down in a markdown or a LaTeX file what's going on? What have you tried up till now? And so I can read it and study it and help you out later. So that tends to be the entire demo. And the point of the demo is that, so most of the people I'm speaking to, they have experience with theorem proving, they're applied mathematicians, and they're basically wondering, will this be relevant to us? Like, is this something that I actually want to use? And my point is that, look, if you're interested in doing middle school math and you're willing to use AI, it's actually quite fun. It seems reasonable. And I also say that it's an open question to me whether it will be usable inside of the kind of math that we use, which is usually probability statistics, convex optimization, and just kind of prove the point. I show them like, okay, this is what it looks. This is what the strong law of large numbers looks like in lean. So they understand that there's going to be a certain amount of complexity kind of implicit in this slide. So that's the demo. And now let's go back to the Putnambench. So the experiment that I did is something that's very simple for any of you to repeat. So there's some code that automates it on 600 problems, but the steps are actually super simple for anyone to perform. So basically, the idea is that each of these agents can be run in a kind of a mode where the UI isn't active. You just sort of give it a prompt and it runs unattended. And in my case, I wanted to pick a very simple prompt. So I basically just tell these agents, there's a file here, it has a sorry in it, can you fix the sorry? I tell it how to compile the file to check if there are any problems. I tell it, if you compile the whole project, there's gonna be a lot of files with sorries, don't get confused by that. And then I just tell it, don't do anything silly, don't introduce axioms, don't change the definitions, and that's it. And so that's the first step. So you'd be doing 3 steps if you're recreating. This is the first step. The next step is that you let it run, and it has a 30-minute budget. Most of these things know when they're finished. I mean, they definitely know when they're finished, so it usually doesn't take the 30 minutes if it's going to solve the problem. But regardless, if it gets to the point where it's hit its budget, you stop the agent, and then there'll be a file, the file that it's trying to fill, and maybe it didn't touch it, maybe it did touch it, doesn't matter. The next thing you do is you compile the file, right? So that means you give it a compiler, and if it returns an error or if it says there are any sorries, then you stop. So that means it didn't score, it didn't get a check mark. But then just to be extra sure, I also run something called Safe Verify, which is a tool that I use. There's many kind of verification tools. And what Safe Verify is doing is it's basically checking the solution with the original problem, making sure, did this thing actually solve the right theorem? Did it change any definitions? Did it, add any axioms? And I think it's fair to ask, like, how much does this cost? So I think there's like a corny joke that mathematicians are machines that turn coffee into proofs. Well, it's, I don't know, maybe like half a cappuccino for one problem. And this Safe Verify is actually useful. I think many people have sort of touched on how lean can be gamed. So there's just like some actual data. So in this case, we have an example where 234 things compiled sorry-free, but when you pass them to Safe Verify, only 203 of them survive. And the issue there is primarily that it's using native decide, which is basically computation, right? There are some other examples where Some of the weaker models use axioms and so forth, but almost all of the issues are just using native decide as a tactic. And I would say most of the instances actually are pretty innocuous. Like, so here's one example. One example of it using native decide, which it says, you know, the GCD of 90 and 92 is 2. I mean, that's fine. In this case, it's much more egregious. It just basically says, well, you know, I can just search the entire space of 1,000 choices using native decide. I'm done. So obviously, a student wouldn't get any points for doing that. And that's basically the issue. It would be very easy to just tell the model, don't use native decide. For me, I didn't know that native decide existed, so it's like a learning experience for me, but you could have told it either don't use native decide or just simply teach it how to use safe verify, and it would do that at the very end. So these tools are very steerable. You can, like, you know, work with them. Once you understand something, you can tell them, you know, go back and like, don't do that again. So then there's the question of, well, okay, what are these bodies, what are these agents actually doing? So because it's running on your laptop, you can really see what's going on. They have log files, you can kind of understand what's going on. And basically what they do is they take your request, they give it to the model, and the model tells them different things to do on your computer. That's kind of the high level description of what's going on. And most of it is running commands on your computer. There's also some other things that it does. So there's maybe 52 times it runs a command on your computer, and 2 times it's doing some internal planning. And it has like a to-do list, and it's updating the to-do list. And this is the commands that were run for a single problem. So this is that same problem that we were looking at before. So the 1992 B1 problem, and it ran for 23 minutes. And so you can see kind of what kinds of commands it's running. So it's running something called RG, which is a command that you can search strings on your computer. So it's kind of like grep. It's just looking for strings in a file. Sed is what it uses to edit a file. So when it needs to edit a file, it's using a very torturous path, but it's quite good at it. I don't know if you've ever tried doing file editing with sed, but it's kind of insane. And then it's calling the compiler, so it calls Lake 6 times. It probably failed 5 times, and at the very end, it finally was able to get the solution. And you know, so basically, the way it does premise selection is a very kind of a crazy way to do it, but it just searches the file system, and it has some common sense, right? So here's a case where it's trying to search for a specific string, and initially it doesn't find anything, but then it kind of looks around the working directory and realizes, like, oh, mathlib is in Lake packages. Let me just look there. Let me like search and like kind of limit the number of results. And so off it goes, and it finds. So this is how it like finds tactics. And I mean, if you didn't have someone to ask, and if you didn't have Zulip, and you didn't have Lugal, well, I mean, this is probably what you would do, and it's quite good at it. So it's not us. It's something that's quite good at doing. Okay, and then I'll just show some more results that I've collected over time. There's a lot more results in a website that I'll show you a little bit later. But this is just one graph of what does it look like when you kind of plot versus decade. I'm not going to try to interpret it for you. It's just that's the data. You can also look at like, okay, how does it vary versus difficulty? There's nothing too surprising there. It is nice that this isn't 0. Here's another chart of, now we're not looking at just at Putnam, we're looking at multiple data sets. So what I've done is I've sampled 50 problems from many different data sets that are similar to Putnam. Putnam is down here. And I've also run many various variations of these agents with different models and different properties. And the 3 points that I'll make out here is that, so all of these data sets, including, so Fate is a family of data sets, but even within this family, all of them use different versions of Lean. These guys don't care about that. Like, they can read compiler messages. If something gets refactored from what they understood, they can see the compiler message and figure out what to do. They're not brittle to the Lean version you're running. Gemini is this light blue, and I would say, in my experience, it's been the weakest of them. So I'm using Gemini CLI with Gemini 2.5 Pro. And I wouldn't say Gemini is a bad model. I think the issue is actually the body that it has is not very good with lean. There's a new model called Gemini 3 Pro, which is very hard to get access to at scale, at least for right now for me. So I will update these numbers. But the simple experiments I've done also seem to suggest that Gemini 3 is also going to have problems. And then I guess the other piece I'll mention is this data set, Fate-X, is probably the closest to professional math. It's meant to be problems that you might encounter in a PhD qualifying exam if you're doing abstract algebra. And you can see none of them are doing pretty good in this most simple baseline that I've been doing. Okay, and then, so obviously my goal was to start with the most simple baseline to try to understand what was going on, but it's very easy to then look at, start doing perturbations. You can look at the literature from the results on the leaderboard, and you can get ideas from there. So one simple perturbation is just feed the agent a natural language proof before you have it go. So this is literally something, again, you could do. You could take the problem statement in LaTeX and give it to ChatGPT 5 Pro, which in my experience has been the strongest natural language mathematician, have it generate a natural language proof. And then when you run your agent, you just say, okay, please discharge this. Sorry, it's the exact same prompt. But also, by the way, there's a LaTeX file here, which has a proof that you can follow. And in that very simple baseline, it seems to have some positive impact. So you go from 203 to 213. And you also see that the collapse from things that compile but then fail safe verify is a little bit less, which sort of makes sense, right? If it has a natural language proof that's been asked to follow, it's much less likely to then just say native decide, I'm done. So if you want to dig into more of these details, you can go to this blog post that we maintain. So the experiment that I'm talking about here is called Three Horsemen, but there's other blog posts. There's things on data sets and kind of ways of forking REPLs and so forth. Please feel free to go there. And finally, I just mentioned some future directions. So started with a very simple baseline. You can really do much more. So these tools are meant to be easy to augment. You can give them extra capabilities using something called MCP or skills. You can use them to delegate to more sophisticated approaches. There's much more than you can do than the baseline. And so I think one thing that would be very fun to do is actually work in collaboration on a real formalization. I think that a good first step would actually be to redo a prior work. So take some piece of work that maybe would take, a day or two of time, and then work alongside a mathematician and just redo it using these agents that are very transparent, collect data, look at the data, kind of talk about it, and try to figure out how to steer these agents to do a better job. And then, other things that are interesting to me are other modalities of using AI, right? So in AI, typically there's three paradigms. There's theorem proving, so discharging saris, there's formalization, and then you also use AI for semantic search. So these are the three main paradigms I've seen. To me, it'd be interesting, based on what I've seen, to think about, okay, well, what would it be like to use AI to write a tactic? Or to engage in other behavior that's more like a mathematician, like conjectures, or if you want to channel your inner John Conway, let's design syntax with an agent. And then going the other direction, what's actually quite interesting to me is pedagogy. So I'm constantly struggling with remembering obscure things about lean. I kind of have to look at a bunch of things in my life, and I always forget. And so I find the natural number game a quite useful introduction. I refuse to hit that hint button, but at some point you really just need hints. And I find it I don't usually go to the Zulip to ask, but if I had an AI, so if I had a system that I could go to the AI and ask it just simple questions about lean, I think that would be fun. This weaving thing is also something I'm interested in. I think it'd be fun to teach middle school kids like some functional programming and also teach them about theorem proving, not about functional programming alone, but also modular arithmetic. But then once you have this inside of Lean, then you can have them engage in behavior more like a mathematician. You could ask them like, hey, go define a triangular weave where you have 3 threads doing something interesting. I don't know what that means. You figure it out. You figure out if the definition is coherent. You figure out some theorems to state and then prove them. So I find that like an interesting possibility of what might be possible with Lean. And I'll just finish with that we are very interested in collaborating and also supporting people. So if any of this sounds interesting to you, just please reach out. We'd be happy to chat.
I think we have time for 1 or 2 questions. Yes.
Thanks for the talk. You mentioned that these things use tools and improving the MCP tools might be useful. What kind of information do you think is useful for these agents? Are there any things which you have to keep asking them to like improve on that would be useful to automate with a tool, say?
So it's interesting, and the few experiments I've used with tools, they tend not to use them. They prefer their Linux tool. I mean, that's a matter of prompting them to know to use the tool. There's also a question of whether that's a good thing to tell them to do. It seems like those tools are, it's an open question whether the Lean LSP MCP server is exactly the right tool it should be using. And then, I mean, I think the smart, like the more experienced models or the more intelligent models, I don't see them doing funny things in a loop. I've asked some hard things, but I mean, honestly, I need a mathematician sitting next to me, and like it would be fun to just like look at it, and you can collect it. So the baseline is super simple, but you get a ton of data. So it's actually a fun experience for the person sitting next to you to understand like, well, this is what's going on with the agent.
Thank you.
Hi. So as someone who left quant finance to do Lean, I'm really interested in terms of like formalization and where you think that fits in the like quant finance side of things.
Yeah, I mean, I think for me, the open question is, can Lean be a tool for exploration, right? So if you think about Lean, maybe one of its reasons for success, it created a user experience that was appealing to mathematicians. And the question I have is like, can the user experience be appealing to applied scientists? And for me, I think there's a less need in applied science to focus on verification of either complicated proofs or software. It's really, can I have a tool that lets me explore quickly? And quite often you're fighting with the theorem prover, so that doesn't help. But you can imagine the workflow could get to a point where I could state an idea, I could prove some results about it, so I'd be more confident about using it or not making a silly mistake and rejecting an idea for an invalid reason. So I think ultimately that's the workflow that I think might be useful in all of quantitative research.
All right. Thank you. Interesting.
Hey Neil, thanks for the talk. So you mentioned in the future directions 2 modalities, writing tactics and conjectures. Both of these things I'm really interested in. Do you have any future plan or something which you'd like to share about both of these directions?
Yeah, it's like, come talk to me and let's figure it out together. There's really no plan. It's just, what I like about these tools is they're very easy to use, they're transparent, and so it opens up a lot of creative possibilities, right? There's a lot of effort goes into fitting a model using GPUs, and that takes a ton of engineering, and this takes no engineering at all. This is like plumbing, so I think I love this. Yeah.
All right, thanks.
Let's thank again Nehal.